So use the operator to solve the d squared y dx squared plus 3dy dx plus 2y is equal to 7 exponential 3x. So in our solution, y will be equal to yc plus yp. This implies what? A d squared plus 3d plus 2 into yc is equal to 0. Auxiliary quadratic equation. It is m squared plus 3m plus 2 is equals to 0. This is m plus 2 into m plus 1 is equals to 0. So m is equals to negative 2 or m is equals to negative 1. Therefore, our yc is a exponential negative 2x plus b exponential negative x. B exponential negative x. But we know something, but d squared plus 3d plus 2, when this one acts on yp, it is the one to give us what? 7 exponential 3x. So this implies our yp will be equal to 1 all over d squared plus 3d plus 2. The whole of this acting on 7 exponential 3x. The whole of that acting on 7 exponential 3x. This 7 is a constant. It can pass any operator. So it comes forward. So we have 1 all over d squared plus 3d plus 2 multiplying exponential 3x. Now because this is a pure exponential function, we will use Theorem 1, which says what? Where there is a d, you insert the a. So this exponential will pass e power 3x. Where there was a d, we insert our a. And our a is now 3. So it will be 3 squared plus 3 times 3 plus 2. So this one gives us 7 exponential 3x into 1 all over 20. 1 all over 20. Just a minute. Not 1 over 20. Yeah, it is 1 over 20. 9 plus 9 plus 1 all over 20. So the answer here is 7 all over 20 exponential 3x. That is our yp. So yp is equal to that. Therefore, the general solution, our y now will be equal to ae exponential negative x, 2x, plus b exponential negative x, plus 7 all over 20 exponential 3x. And that is the solution to that differential equation, which ends at general solution, since there were no conditions or boundary conditions given. So in our example, so solve the d squared x dt squared plus 4dx dt plus 4x is equal to 5 exponential negative 2t using the operator method. Using the operator. So in our solution, we are dealing with the dx dt. So x is a function of t. So x will be equal to xc plus xp. This implies what? Our d squared plus 4d plus 4 into x. Into x should be equal to 0. Auxiliary quadratic equation will be m squared plus 4m plus 4 is equals to 0. This is m plus 2 into m plus 2 is equals to 0. Therefore, m is equal to -2, which is appearing twice. It's appearing twice. This implies that our xc will be equal to e power minus 2t into at plus b into at plus b. But we know something. But d squared plus 4d plus 4 into xp, this is the one to generate. This is the one to generate 5 exponential negative 2t. So xp will be equal to 1 all over d squared plus 4d plus 4. The whole of this acting on 5 exponential negative 2t, which is equals to 5 into 1 all over d squared plus 4d plus 4. This one acting on exponential negative 2t. Because that is a pure exponential, we use theorem 1. So we are going to have a scenario where this exponential 2t passes. We have 1 all over. Where there is d, we insert a, and our a is -2. So it is -2 squared plus 4 into -2 plus 4, which is equals to 5 exponential negative 2t into 1 all over 0. So this one there is a question mark because 1 over 0 does not exist. It is an infinite value. So we say theorem 1 has failed. Theorem 1 has failed. And if it has failed, now we are going to use theorem 2. We are going to use theorem 2. So we go back and pick it where we had xp is equals to 5 into 1 all over d squared plus 4d plus 4d plus 4. The whole of this acting on exponential negative 2t. And since we don't have another function, we assume there is some function near this one, which is 1. Because 1 times exponential negative 2t, it is exponential negative 2t. So this one will be equal to 5. We now use theorem 2. The exponential will pass. That is exponential negative 2t. Where there was d now, we put d plus a. And our a is what? Our a is -2. D plus a, it is d plus -2, which is d minus 2. So squared. Plus 4 into d plus a, d plus -2, which is d minus 2. Plus 4. The whole of this acting on what? On 1. Which will be equal to 5 exponential negative 2t. We have 1 all over. We will have now, we expand this is d squared minus 4d plus 4. Plus 4d minus 8. now plus 4. The whole of this acting on what? 1, which is equals to 5 exponential negative 2t. Then we remain with 1 all only over d squared acting on 1. 1 all over d squared acting on what? 1. Which will be equal to 5 exponential negative 2t. This is the same as 1 over d multiplying another 1 over d multiplying 1, which is 5 exponential negative 2t, 1 all over d. Then we now the first 1 over d, we integrate 1 with respect to t, which is equals to 5 exponential negative 2t, 1 over d, the integral of 1 dt, we get t, which is now 5 exponential negative 2t. 1 over d times t is the integral of t. And when you integrate t, we get t squared all over what? 2. So the expression for xp is now equal to 5 all over 2 t squared exponential negative 2t. That is the expression for our particular integral. The general solution, therefore, will be given by, the general solution will now be given by, general solution, x will now be equal to a power minus 2t into at plus b plus 5 all over 2 t squared exponential negative 2t. And that is the end of that solution of the differential equation. That's the end. So example 5, use the operator to solve the d squared y dx squared minus dy dx minus 2y is equal to 4 cos 3x is equals to 4 cos 3x. So in our solution, we say y will be equal to yc plus yp. This implies what? D squared minus d minus 2 into yc is equal to 0. So AQE, we have m squared minus m minus 2 is equal to 0. So this is m minus 2 into m plus 1 is equals to 0. So m is equals to 2 or m is equals to negative 1. Therefore, yc will be ae power 2x plus be power negative x power negative x. So we say, but we know something. D squared minus d minus 2 into yp is what will be equated to 4 cos 3x. This implies what? Yp alone will be equal to 1 all over d squared minus d minus 2. This one acting on 4 cos 3x, which will be equal to 4 into 1 all over d squared minus d minus 2 multiplying cos 3x, which is equals to 4. We have that one 4. We are now going to apply theorem 3 because this is a pure trigonometric term. We take the a, which is 3, we square. 3 squared is 9. Then we give it a negative sign. As we give it a negative sign, we replace where there was d squared. So this will be 1 all over a minus 9 minus d minus 2, the whole multiplying, acting on cos 3x, which will be equal to 4 into negative 11 minus d, acting on cos 3x. Now, since d is in the denominator, we cannot take this one to the numerator using binomial expansion, since when you differentiate cos 3x, there is no one time it will go to 0 even if you differentiate it 1,000,000 times. So the only way we can solve this is now to remove the d that we are having in this denominator and either create a d square through rationalization of this particular fraction. So we rationalize this. So we say this is 1. And when we want to rationalize, where there is a minus d, we are going to multiply with something that looks like a conjugate. So where there is a minus d, we are going to replace with the plus d, whatever. So this will be 1. This one we can multiply both numerator and denominator by minus 11 plus d. Here we have minus 11 minus d into minus 11 plus d. Now multiplying cos what? 3x, which is equals to 4 into, this is, we can just say that is d minus 11, the numerator. This one, if we multiply, we get 121 minus d squared. 121 minus d squared. If we multiply out this, we get 121 minus d squared. Yeah. So this one acting on cos 3x. Since there is another d squared which have resurfaced in our expression, we again apply theorem number 3. We again apply theorem number 3 dealing with pure trigonometric functions, so that we can clear the d squared. So this one will be equal to 4 into d minus 11 all over 121 minus, where there is d squared, we take a square and we give it a minus sign. So it will be minus 9. It will be minus 9. We insert there. The whole of this acting on cos 3x. The whole of that acting on cos 3x, which will be 4 into d minus 11 all over 130. All over 130 acting on cos 3x, which will be 4 all over 130 into d times cos 3x, we get minus 3 sin 3x. Minus 11 times cos 3x, we get minus 11 cos 3x, which simplifies to 2 all over 65. 2 all over 65. We can put a negative out, and then we have here 3 sine 3x plus 11 cos 3x. That's 11 cos 3x. So this is our yp. Therefore, the general solution, y is equals to yc plus yp, which will be equal to what? We had ae power 2x plus be power minus x minus 2 all over 65 into 3 sine 3x plus 11 cos 3x. And that is now the said solution to that differential equation when solved using the operator. So for today we are going to end there. We have got one or two examples to clear this, so that we are through with the now differential equations as per the syllabus, as per the next syllabus. So we'll have cleared second order using the method of undetermined, and now we are doing the operator.